And I had this thing. Let's see. Oh, the homework. So let's see. I didn't grade them all. I mean, I graded a couple. So I didn't really grade many. So let's see. Actually, I should do this. Someone in the other class taught me how to do this. Right. So I went through that in class, right? I think everyone, I mean, mostly the ones I looked at, people got that. Hi, what's going? And what's the difference between optical and acoustic? Um, People got that, except that stiffness is only acoustic, but heat capacity is both. The heat capacity is optical and acoustic. So, I mean, these are kind of like multiple choice questions almost.
You don't want long. You want long answers.
No, you could get a long answer if you wanted, you know, but there are up to G here, so it's not five. There's like seven questions. So I think those two are like freebies supposedly. So each one's only worth 14 points instead of 20. Too. So if you got it kind of totally wrong, it's probably like -7. Unless you really, really got it wrong. It's more than that. So anyway, then he says vibrational frequency is proportional to the square root of stiffness. So that's the thing with the force is mass times acceleration, or the spring minus spring constant times the distance, and then you plug in sine of theta, sine of omega t for the argument, and then the first derivative is cosine times omega. The second derivative is omega squared minus omega squared cosine minus omega squared sine, and then the signs drop out and you just have omega squared as the modulus times the divided by the whatever mass, and then take the square root of it. So you had to say something. I mean, one of the two that I graded like parroted whatever I said. It didn't put in the thing about the derivative of the sine, because that's kind of the whole point of it. That you get when you take the derivatives. Yeah, you get the same thing back and it cancels out. So you have a sign in the answer. Yeah, and then you get the negative, and you also get the square of the frequency, which is the point of the whole thing. So you can't, without saying sine and doing the derivative, you can't get that answer. Even if you wrote down, here's the equation, here's the thing, that's what it comes out to. In my opinion, I guess. So then this thing, calculate the device stiffness, that's, I added that to the notes. So that's like slide 88 now, this thing. So that's from that paper. He does it, let's see, I think this is from the same paper. So he does it the other way, or wherever this is from somewhere else, I think, but
That's the same one.
this is from that paper.
Mm-hmm.
Okay. Anyway, he's using it to calculate the Debye temperature from the modulus, but we're using it to calculate the modulus from the Debye temperature. The Debye temperature can be obtained from the Debye frequency, right? So if you know the frequency, you can get the temperature, then you get the modulus. So I guess some people did that. All right, so that's that thing. And then let's see, back over here. So then I went through this in class, right? This has to do with the density of states, and it's got certain features in it that when you at lower and higher temperature, it activates the different features. And so low temperature, this high frequency thing isn't there. High temperatures, it shows up because you have higher frequencies, higher energy, so it activates those vibrations. And then the behavior swaps between diamond and graphite because of that swapping of the density of states. I think people got that. I mean, I said it in class. I think people kind of figured it out. And then at least I only graded 2, so I think both got it. Derived equation 3. So this this is just do that derivation that I did in class, or you could do it some other way, but you had to derive it. I mean, in a believable way, like something that could be read. Let's just stuff that in here. This is just, it's like, oops, yeah. It's like something called divine model or something. No. I did a lot of stuff. Right. One of these has a divine model for specific heat. I guess that's it. With the, yeah, with the picture of the vibration. This is kind of what I followed. It's like it isn't. I mean, it's. I think it's a better the way I did it, but basically it's here. I put a link for this also into the notes too, because there's a bunch of derivations of this actually in the notes, but none of them are that readable. And then this thing I think is kind of straightforward. So there's a bunch of different derivations for it. But like if you go to the wiki page, there's also three derivations, right? For there's a wiki page, divine model. That's also is called the divine model. So it's like one derivation, two derivation, three derivation. So you could have used any of those three, but one of the groups didn't use any of those three. It's like, or the Libra text one. So there's, you had your options. You know? If you want to go back and do it, it's okay. I'll look at it again or something. But anyway, so and then how does it differ from the thing before equation two? The thing before equation two is just the Einstein model. Like this, if you said CP, that's the Einstein equation. So what he's doing is saying he's got a bunch of Einstein equations, and then he's going to integrate them up to the Debye temperature using this 1 over t squared, which is like the weighting of the, in other words, when you do the density of states for the Debye, the density of states for the Debye heat capacity is 1 over t squared. It's nu squared over t squared. So this thing, that thing in the brackets is a density of states. And he's saying like for each density of state for the frequency, you can use a Debye model. I mean, the way it's worked out. I mean, you could derive it that way too if you wanted. You say like, well, you'd have to derive the density of states for the Debye model first, which is this term. And then for each frequency, it's going to contribute one Einstein vibration. So Einstein says is one vibration, Debye says is a spectrum of them. Actually, this is a pretty good equation because of that, you know. So anyway, that's it. Something like that. I mean, it's just blah 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 about Einstein and Debye, and kind of, and then it's like, what is the difference between the two? No, it doesn't even say that. How does it differ from equation? It says so. Basically, one frequency versus a spectrum. That's the idea, I mean, the way he did it, it kind of points out that this thing, if you derive it, that not exactly derive, you just state it that way. There's an integral of Einstein's in the weighting factors, the density of states for the Debye, which is going to be this higher frequency, and then you get to the Debye temperature and just cuts off. Right? It's like it's in here someplace. 588, 89. So somewhere in here. Here, that's it. So that's the density of states for the, right? So it's frequency squared, should be over temperature squared. So that's basically the density of states for the, so that's where he gets that thing. That's basically the density of states. So anyway, so that business, and then explain how he obtains the Debye temperature. I went through that in class too, but basically he does his simulation using the VASP density functional theory. And then he calculates the vibrations from that, and then gets the density of states, integrates density of states, and then gets the heat capacity. And once he has the heat capacity, he fits it with the wherever the Debye equation is, and he gets the Debye temperature from that Debye equation. So he does a fit. He does a fit to get the Debye temperature out of it. At high temperature, where you get the anyway. So that's kind of how he gets it. That's how he gets it. So that's that one. Anyway, so hopefully that's okay. But like I said, I only graded 2 of them, so it's like one did exactly what I just said, and the other one didn't. You know, it's just hard to tell how people did on it. All right, so I was just gonna. So this week there's just something about Brillouin scattering. So just some questions about Brillouin, and then let's see. So there's a Brillouin scattering, Brillouin, pronounce it wrong, Brillouin, like Brillo pad eon, Brillouin. But there's an instrument for that in the department that or in the chemical engineering department. John Nichols has this machine, and he said, let's see. He said Tuesday is better, but I need to align it. So he said next week, Tuesday. But I have that other class after this class at 3 o'clock. Oh, okay. Well, then maybe it's going to be on Thursday. He hasn't said. Let's see. I'll have to tell him. Let me tell him that. You guys can do it 3 o'clock though, right? Generally, Tuesday, Thursday. You can't do on Thursday. Okay. Tuesday is a holiday. This coming Tuesday is a holiday. It's a reading day. So I'll forget otherwise. So maybe anyway, we can look at it. It's kind of interesting to see. So it's gonna so basically so we're gonna get, let's see, let me get back here. Oh, hard to tell where that is. Right before that. It's a nice thing with Brillion and Raman in it. It's from this paper. Actually, it's from this homework, so but it's not written here. This is a review paper. And so here, this is a pretty good photo because it shows that Raman spectroscopy and Brillion are the same, kind of the same thing, and put them on the same plot. And Brillion's doing acoustic, Raman's doing optical, and Brillion's doing low frequency, so it's kind of like near IR, and Raman's doing kind of optical wavelengths, some normal wavelengths. So let's see. Just briefly kind of mention that. So you have light coming in. It's got an electric field that's going up and down, magnetic right hand rule to it. So you have like whatever direction electric field, magnetic goes with your fingers like that. Right. So if you have an oscillating electric, magnetics, it's out of phase by 90 degrees. So when the electric goes to 0, the magnetic's maximum. Magnetic goes to 0, electric's maximum. So that's electromagnetic wave, right? So if you have like
You turn on the brightness on the.
all right. The pen is there though. That's good.
It's because of the lamp.
Oh, focus.
Yeah. The focus on the lamp.
There you go.
Okay.
Okay. The lamp didn't seem to help. That's worse, right?
Yeah.
Freeze. Brightness. Brightness. Yeah. Weird, huh?
Oh,
But it's like X-ray vision. If you go far enough, you can see through the paper. If you get to exactly the right point. Somewhere like that is all right. Oh, I know. All right, wait. I can see what's going on now. I got the background light on.
There you go.
Yeah, we got the technology. All right. So anyway, it's coming in and you have like something like NaCl, so that's polar. It's that electric field, so is going to pull these guys in kind of opposite directions, right? And then they're going to oscillate. Right. So that's what IR is. You have like a vibration. That's happening in the optical, what's happening in the IR wavelengths. Right? So anyway, so that's polar. You have polar groups. So if you have like a carboxyl group, it's got like del minus, something like that is going to have a really strong IR band in it. So you have a del minus, del plus. What else? That's like a classic one. I mean, all the bonds like carbon hydrogen will have an IR band in it. And carbon has an IR band, and double bond has a band. So these are like 3,000 inverse centimeter, and this thing's like 600. So whatever I guess this is lower energy than that. So it's a tighter bond, or I don't know. Somehow they're at different frequencies, and it has to do with the mass of the atoms. It has to do with the strength of the bond. Right, so it's just a mechanical vibration kind of idea of things, and also the geometry. So if you have CO2, that's linear. You have H2O, that's not linear. So this has more vibrations in it than that does. So the number of vibrations has to do with the shape of the molecule. It's got to do with the strength and the position of the vibrations is the number of atoms, the shape of the molecule have to do with how many vibrations, and the polarity of the bonds, and the strength of the bonds, and the mass of the atoms tell you the position, like what wave number they're going to be. And these are quantized because it's atomic level. The energies for these vibrations are quantized. So there should be, if you looked at this and you said like absorption versus wave number, you should just see spikes, but you don't. You see these kind of broad peaks in IR. Right, so they're quantized, but there's some kind of wishy-washiness to it. Orientation is going to matter, like this. So if it's oriented perpendicular to the thing, there's not going to be any shaking, right? And then as it gradually comes into orientation, you get more and more. So maybe the energy of absorption changes with the angle. Also, the local environment for polarity, maybe it changes a little bit. So for whatever reason, the peaks are broadened. They aren't just spikes. Here you see a plot of absorption versus wave number, and usually the high wave number, usually this scales backwards, like the K. So it's like 2,000. Let's see, how does this work? Usually this scales backwards. 2,000 is there, 600 is here, so that looks forward. Anyway, for whatever reason, that's usually a backward scale in IR. And then you can have an absorption, or you can have like transmission. So if the beam comes through, and you had intensity 1, intensity 0, and you have the intensity of the band, then intensity of the band at whatever frequency over intensity 0 at that frequency, that's the transmission value, right? So that's, if you plot that, that's going to look like dips. Every time you have a peak here, it's going to be a dip, right? So it'll be like that. And absorption has to do with like e to the minus thickness of the absorption coefficient, and then some kind of prefactor is going to be the absorption, right? So basically, the absorption coefficient is going to be kind of like the transmission. So it's almost like a exponential of the transmission will be the absorption. So it's going to be like, this gives you Beer's law, I guess, which is like ln of the absorption is like the thickness of the sample times the absorption coefficient. So basically, the shape of the two curves for transmission and transmission's upside down of absorption, and then absorption, the shape of the curve is going to be a little bit different because one's going to be a log of the other one. So, but basically they're measuring the same thing. So if you look in that, so anyway, IR can be done either way. Raman is usually done with absorption. So you have straight, so that's what this plot is, an absorption plot. All right. This is basically the peaks are where the absorption happened. So it's peaks and he says scattering intensity. Basically, if this was IR, this would be absorption. Like you'd have peaks up means there was an absorption event that happened. Okay, it's called scattering intensity because in Raman and Brillion, which I pronounce wrong all the time. So Raman, Brill, then I don't remember the rest of it. OU on, IOU on. I think it's like that. Brillion. Right. So these two guys are going to be scattering events. So the beam comes. So when you have a scattering event, you still have an electromagnetic wave coming in, and you still have. But here you're looking at systems where you have like a lot of electron mobility. So electrons can like fly around in a benzene ring, or if you have a conjugated system like that, or if you have like graphene or something, or graphite, where you have, it's all totally conjugated, so everything's like every other bond's double. So the reason when it's like that, this has a resonance structure with the double bonds on the other ones, like you can flip over. Right, so the electrons can flip, they can jump from one bond to the next bond to the next bond. In fact, they're jumping all the time. Right, so if you try to pick an electron here, it'll move to the other one. So that this is stable because if you try to react an electron here with some other, like some cation, it's not, when a cation tries to get that electron to neutralize itself, the electron just pops away, like it's like trying to grab a greased pole or something. It squeezes away, or a pumpkin seed, right? So because of that, that's chemically like super stable. And when you have this kind of conjugation in it, also it's conductive in the direction of going around the ring. So it's got a magnetic moment even normal to the ring, right? And also because it's got this hopping thing, it has to be in a plane. So this sp2 thing is a planar bond. So it has to be totally planar. So if you have graphite, the whole thing is a planar structure. Anyway, so when this guy comes in, he can make, because it's going to be like a plus minus field here, he can make the electrons all go to one side. So then that's polarized. You've just polarized the molecule. So the parameter. So in this case, the parameter is the polarity. It's like NaCl has a lot of polarity. Here it's polarizability. And usually the two are opposite, like grease is not polar and salt is. But salt is not polarizable because the NaCl, the Cl is holding onto the electrons and the Na doesn't want the electrons. Right. So, but in this case, it's nonpolar because basically the aromatic things like oil, like the nonpolar molecules. There's some cases where you have polarizable and polar, but in most cases they're total opposites each other, which means that so if Raman is sensitive to polarizability and IR is sensitive to polarity and they're opposite extremes, then if you run both, they complement each other. So you can see all the bonds if you run the two techniques, right? But the two techniques are quite a bit different. So in Raman, you come in with this, and then you're shaking and baking the electrons, right? with the same frequency of the thing that came in, right? And if that, when that thing will act like a little generator, so it's generating the same electric field, oscillating electric field, like that sine omega t thing, in all directions. You come in, it's like you come in with the sympathetic frequency of the bell, and then the bell rings, but the bell rings not in the direction that your sympathetic frequency came in, but in all directions. So it emits it out like all the way like that. So if the frequency going out is the same as the frequency coming in, that's called elastic, because there's no change in energy. H nu is the same for the in and out. So there's no change in energy. That can be models if you had a billiard ball coming in, hit the bunker and bounced off. Right, so it'd be like Bragg's law, that the D is going to be lambda by 2 sine of the angle. Right, so the angle that you come off at, it came off from some kind of lattice planes that they constructively interfere at that angle. Right, so that's elastic scattering, Bragg's law. Right, so if you have some kind of spacing in a little peak, and the peak's associated with the wavelength that came in, wavelength or the frequency that came in, right? If the wavelength of the frequency that came in changes in the event, then you can't get an interference pattern. You can't get Bragg's law. You can't measure any size with it because the thing absorbed or gave up energy, right? So it can either accept the energy, some energy, or release some energy. And if it does, then if you do a spectrum of what comes out at some angle, so if you have like the frequency, then the spike of the thing, and then you're going to have an increase in the frequency of the energy or a decrease in the frequency of the energy. So the decreases, that's called Stokes. That increases is called anti-Stokes. So why would it decrease or increase energy? It's because it vibrated. Just like in IR, it vibrated, but in IR, you directly take the energy of the vibration, and it's at that frequency that you absorb it. Here, you can come in with some other frequency radiation, and you're looking at the change in frequency for these side peaks on it. Right, and that change, that delta frequency, that's your absorption energy. And that can be positive or negative because it could already be thermally shaking like crazy, and then just dump that energy into your light that goes out, and then you've increased the frequency of what came in. Or it could be sitting there standing still, and then it sucks off some of that energy from the light that came in, and then you've depleted it, and then you have a lower frequency light that comes out. Right, so these are small shifts that happen. Right, so that's the Raman. So, but the change in frequency here is going to be the same as the frequency on the IR plot. It's a frequency where it absorbed at IR is going to be the same as the change in frequency here. So you can come in. So with IR, you might come in with like a tungsten lamp, like you have. It's going to be heat. Like IR is heat, so you're going to come in with something that glows like hot. It's going to be glowing in. It's going to be absorbing. So you need monochromatic hot. So put it through a prism or something. It's going to absorb certain frequencies in that, and they'll be quantized. There'll be spikes, right? Because in an atomic level, it's going to be quantized. And then for this, you can come in with the laser, like any big laser. So here you can come in with a really bright thing, like should be much stronger technique than IR, except this Stokes and anti-Stokes thing is a pretty weak thing. So although you're coming in with a bright laser to excite this thing, your measurement's going to be a small little shift of these side peaks of that bright laser. So often discerning something weak next to something bright is difficult, right? So that's usually the problem with diffraction. Like if you try to use Bragg's law and get to something very large, and you have to go to really small angles. And then when you get to small angles, the incident beam is really bright compared to that diffraction beam. In other words, 10,000 times brighter. So it's hard to resolve it at small angles because you're measuring right into the footprint of the thing that came in. Right, so there's only a physical limit to how big you can measure with Bragg's law. Small as you can measure is going to be lambda by 2, so that's fixed. Or the sine could go to 1, and we have lambda by 2, and that's it. Right, so anyway, so Raman is a scattering event. It's an inelastic scattering event. You have elastic scattering going on, but you get these inelastic side peaks, and the delta nu is going to be the energy that was absorbed by that quantized vibration of the molecule that had to do with the polarizability of the electrons and the bonds. So you can see this is something that chemists would use because it's got to do with benzene rings. Metallurgists are not that interested in Raman exactly, right? And IR both because salt, it's kind of like metallurgy. You could get, it's partly half metal, right? It's got Na in it. So basically both IR and Raman are kind of like your classic chemistry lab things, stuff this stuff in it, run the spectrum, fingerprint it, bingo. Because it's quantized things, you can tell which groups are in it, what chemical groups are in it. Take the chemical groups, do like a jigsaw puzzle and put together the molecule. Right. NMR is another spectroscopy that couples with that. With NMR, you can tell like this molecule is in my hand and this one is in my elbow. Like you can tell the relationship between where, it's more than just a jigsaw puzzle of the groups. It's like you can actually tell that the hand is here and the elbow is there. Right. So did you see the artificial intelligence and the there's books being published, I guess, of art books, and it's like they'll come out with like 3 fingers instead of 5, things like that. And the elbow isn't by the hand, it's somewhere else. But they look just like a person, but it's kind of like something weird. And apparently the only way you can tell, well, first off, the name of the book is going to be something that you can tell it's artificial intelligence made, so it isn't a real nationality or something. It's just going to be like a hybrid of Japanese and whatever. And then if you look at the pictures, they're going to be some kind of odd thing. It isn't human, or it's not really the flowers where the eye is supposed to be or something like that. Anyway, so it's the same thing. Like IR is kind of an artificial intelligence analysis, and the NMR is actually you figuring out exactly what the thing is. You can tell where everything is. Anyway, so beryllium is the same thing as Raman, almost exactly the same thing, except it's for metallurgists. Okay, so metallurgists are not interested in aromatic rings. They aren't really interested in optical phonons. They're interested in like modulus and things, right? So basically acoustic. So the same thing, a beam comes in, it's in a low frequency, so it's like IR frequency. This is kind of optical. Oh, sorry. Okay. I thought I just did that. There, I didn't hit the project thing. Anyway, so this is that review paper for the homework, but basically, so it's the same technique. So you have the same thing. So scattered intensity here means of the peak, scattering intensity of that side peak, of the inelastic peak, not the main. So the main peak, you have a scattering peak at some angle. You just kind of fix that. You aren't really interested in Bragg's law like this. So if you change the angle of scattering, it's like Bragg's law, you're changing this probe size, or you're looking at the materials. You go to smaller angle, the probe distance gets larger and larger. Go to large angle and it's small. So basically you're going to be looking at 90 degrees, just some oddball angle, or you could backscatter with this. Maybe you aren't interested in how the angle relates to the scattering beam, because with an elastic, you can't use Bragg's law because you don't have a fixed wavelength. Right? Without a fixed wavelength, you can't use Bragg's laws, you can't do diffraction. Right? So here, it's an inelastic event, so it's inelastic scattered intensity versus the energy shift from the peak that went in to the peaks you're measuring. And the same thing can happen, except it isn't the bonds, the electrons and the bonds that are vibrating, it's the actual crystal structure, like the acoustic phonon of the crystal structure vibrating. And that thing's like a lot lower energy than the energy that it takes to move an electron. Like the smaller you try to move something, the more energy it takes. So if you try to grind up flour and you keep grinding it, it's going to take more and more energy until you can't put any more energy into it. Like you can't grind to an atom because the energy is too high, right? So also things re-agglomerate. But so anyway, so this is lower energy because basically it's bigger. It's a motion of the atoms in the crystal. It's not the electrons. Still quantized, so it's a phonon. These are electron vibration translations. vibrations, basically, not translations. And this is a phonon. Yes. Oh, I thought you had a hand up, but all right. Your hand is up.
Oh,
Yeah, that's a sign in certain cultures. Okay, that's also a sign. All right, so anyway, that's the whole deal on this. So there's one of these machines downstairs. You'll see it's like a laser and like a bunch of optical stuff. And he said he could demo some crystal vibrations, like measuring. All right, so the other thing to say is that no one has a brilliant scattering machine, like virtually nobody. Like you'll be hard pressed to find people with this machine. Everybody has a Raman, or virtually everybody has an IR, and then of that 1 in 10 has a Raman. And of that 1 in a billion has a Boolean, right? So they won't even hear the word, you know. But on the other hand, in physics, it's important, you know. So physics citing people, maybe your odds go up by a factor of 10 or something. So basically there is this kind of thing like IR is very popular. Raman's pretty popular because it complements IR. So IR would be on the same spectral range as Raman, but you wouldn't see the same peaks. You'd see the polar peaks. This is the polarizable peaks. And then this is on a different spectral range, looking at the acoustic. Yeah.
So, that means the Boolean scattering can be ignored at the Raman scattering signal. Almost there is a lot of error signal in this Raman scattering. So I think the Booleans can be ignored because they are so small. So how can the machine can catch that signal? Is there any explanation at the article?
Yeah, I think this is like a 10-page review, I think. So I think it's explained in here somewhere. But I think if you're picking the right frequency, I don't know. Oh yeah, all right. How do you measure this? That's a pretty good question though. So basically you're going to use an interferometer to measure this thing, right? So anyway, so there's 3 ways to measure spectrum, right? So they come in with sunlight, and then you want to separate it into the rainbow. So you can put a diffraction grid in. So optical grid is just going to be a bunch of lines, and then you can rotate it, and then it'll at different angles is going to just follow Bragg's law, right? So you get you'll get a peak when you have the spacing on your grid equals so when the angle, the wavelength, so you're going to be picking out the wavelength with your grid size and the angle. So if you have slits here, you can get the colors if you rotate the thing. That's a grid, or it's diffraction. So you can have a monochromator for X-rays. It's a crystal, and you can crystal monochromator, same thing. So that's a spectrometer, right? Then the other way, you can use a prism. So you can use Snell's law, like n sine whatever equals n sine whatever, right? So you can, depending on how the light comes in, it'll spread it out. That's just your classic rainbow thing, right? Your sunlight comes in. And then the third way is an interferometer. So with that, you come in, you have a mirror that's part mirror and part not mirror. Right? So some of the light can keep going, and this thing goes up. And there's another mirror here. This was invented in Cleveland, by the way. So Michaelis-Menten interferometer. And like, I don't know when, but Cleveland, the physics in case was like the top thing for a long time. Maybe it still is, I don't know, but anyway. So the beam of light goes up, comes back down, and then recombines with the other one through this kind of half mirror thing. And the wavelength of light is like a micron, right? So if you have a motor that can move a micron, so a stepper motor, which they exist, and you can buy it. Actually, if you take an inkjet printer, it's full of stepper motors. You just take that apart, you can make an interferometer. You need a couple optical components like a mirror. right? So, and then this will do, if you scan through this distance, whatever R here, then you're going to end up when the R is related to the wavelength exactly, you'll get a spike. Like it'll be constructive interference between the bounced one and the one coming in. And then you'll get total destructive interference, meaning that your waves are opposite. This would be the reflected one, and this is the direct one. Right, so they would totally cancel, so you get 0. And then as you scan through, you get like a series of like spikes from it, if it's monochromatic. If it's polychromatic, you're actually scanning through the Fourier transform of the spectrum of the thing. So you'll get as a decay pattern. So you get a noise pattern. So if it's not monochromatic, if it's daylight, you'll get like something like that. It'll just be a noise pattern. Right. And but that noise pattern is composed of a bunch of these sine wave things. So you could say, like, if I could sum up all the sine waves of whatever new distance or whatever, lambda distance by lambda or whatever, 2 pi. So if I could sum up every of these sine waves with their amplitudes, then I would get that decay pattern that I measured in this Michel's-Menten interferometer, right? Just all I'm doing is running my inkjet printer motor up and down. Just goes zzz, 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 right? And actually, when you're running an interferometer, it makes that noise like zzz, zzz, zzz. So it's just scanning through it, So anyway, so you get that noise pattern, and it's composed of a bunch of sine waves. So you can mathematically deconvolute all those sine waves with a Fourier transform, and then you can separate the amplitudes of each of the sine waves versus the frequency. And then you can plot amplitude versus frequency, and that's basically the pattern that we get. So this thing has some advantages, like both these techniques. So you have 100% going through here, and once you go through the grid, you have like 0.000%. You have almost nothing comes through. Same with this. You have 100%, and depending on how good you separate into pieces, the better you separate, the less intensity you get. So you lose. Here, you come in with all the intensity, and you go out with all the intensity, right? So basically, you haven't lost anything in this. So this should get a lot more firepower to it when you get out of this interferometer. There's some problems with the interferometer. So when you get to like high-end IR and Raman machines, they're going to go back to using either a grid or some crystal thing, usually a grid. The medium end ones all used interferometers. That's kind of how it works. So it went so you have like FTIR uses this interferometer to Fourier transform a noise pattern back into your signal. And then so FTIR was like, before there was an IR that had like a grid in it, and that was like your run-of-the-mill IR. And then like in 1980 or something, or 90, whatever, then all of a sudden everyone bought FTIRs. They were more expensive, but they were better because they got more flux out of it. And then now, like if you really are into IR and you get the best one, they're using grids because they have higher resolution, higher spectral resolution than the FTIR. There's some reason for that. There's certain reasons for that business, but anyway, so that's kind of the picture of this thing, where this is coming from. So it is like a analytic kind of thing going on. Anyway, so then you can get these patterns, and that's kind of where this is going. So let's see. Well, my computer says 215. That's what I was wondering. It's like 215 would be bad. I'll double check this one. This thing says 215. This is 115. That's good.
We'll be ready to see.
Oh. Is it this weekend? Yeah, November 5th or something. Man, that creeps up on you. Huh? But they were going to make it change the law or something, right? On that.
In Arizona, it's not a thing.
I mean, it used to be Indiana didn't have it either. But
Yeah.
text. All right, so that's that business. That's kind of the story with that. Oh, here, slide 88. that's this slide, right? So that's okay. We did that. So I'm just going to go through these. We're kind of almost done with this chapter, but somehow I think it will never end. It's 3 weeks, right, on one chapter. So heat capacity is important. We'll do other stuff, but basically heat capacity is kind of a bread and butter of this stuff. So yeah, so this is this business in the chapter about getting CP, which you measure with a DSC, and then CV, which you kind of measure. We're measuring CV with the spectra, and we're also with simulations, the density functional theory stuff, and so a lot of the calc, and then Debye and Einstein are all CV, and CP is like DSC basically. So anyway, we have that equation we got before, and then basically sometimes you don't know the bulk compressibility, or sometimes you don't know either the thermal expansion or the bulk compressibility. So then you need to do the Gruson parameter thing, Grun-Eisen parameter, green iron, I guess, parameter. But it's basically just a fudge factor to get this, the difference between these guys. Right, so that's listed in the wherever the table of these things. No, that isn't that. That is a different gamma. This is the electron gamma. This is the Grun-Eisen parameter, which so there was a homework in the past just about the Grun-Eisen parameter, but we didn't do that this year. But basically, there is a homework on that. If you want to look more into it. It is a subject that people write papers on, so and then there's a couple of relationships to get that difference. That's all. And that's in the book, it's kind of in the book. Then there's this business about, so all the stuff with Debye and Einstein is harmonic vibrations, is anharmonic, which has something to do with basically they say the anharmonic is like thermal expansion, thermal conductivity. But anyway, so and this is like a plot in the book showing for molybdenum and tungsten how the this kind of anharmonic component of the heat capacity, like how much it contributes to it, which seems to be quite a bit when you get to, I don't know, near the melting point, I guess. So there's that business. There's kind of like nuances to heat capacity at the end of the chapter. Then kind of I've already gone through that spectroscopic thing I talked about. So this is showing, this is from the book. So it's like, this is IR shown in transmittance. So, or it could be absorbance if it was written in absorbance. So kind of log of that 1 over would give you, so it'd be an inverse of that, would look just like the Raman curve. Right? They both have, they look like they're pretty quantized, but if you look at an NMR pattern, which is a nuclear spin, which is really quantized, they're just straight lines. And here, this is pretty broad, right? So, and some of these are like really broad, like things like a carbonyl peak or something is a really broad water absorption. This covers a huge range in IR. So anyway, it's quantized, but it's got these kind of broad peaks in it. So for whatever reason. Anyway, so you can see this is the optical transitions, and he has them labeled, and it's like some of them are the same in IR and Raman, like IO1, then IO2 is only in IR, IO4 is only in IR, and IO3 is only in Raman. Right? And from those, you can calculate the heat capacity from the energy of those, because those will give you the vibrational density states with the different vibrations in the system, and then you can integrate the density states using I think we had this function before. This is a number of things at energy h nu, and then they're distributed by the Bose-Einstein distribution curve. That's like the kind of the partition function for that. So when you integrate it, you have how many, their energy of each one, that'll give you the total energy, derivative of the temperature gives you heat capacity. Right, so this density of states you get from these curves. So you can get that either from Brillion or from Raman IR, or from Raman IR Brillion combined, and then get the density of states, or you can calculate with a simulation, like a density functional theory calculation, then get the density of states, then get the heat capacity. So in this case, you can break it apart into acoustic, optic, and then total contributions to the heat capacity. Right. So anyway, that's that picture. This is a picture about Brillion. That's from that paper too, showing the scattering from the vibrations. Shows kind of the Stokes and anti-Stokes shifts for the peak, and then that we already looked at. Right, so that's kind of that business. No, sure. Let me look at what's in that homework here. Oops. Figure 2 raw data, Stokes and anti-Stokes. So I have to go through this one after. There's a lot in this. You have to go through it. All right, I'm gonna have to go through that later. Remember all that stuff. So, all right. This is just the heat. So you can calculate. So since the heat capacity, we're calculating heat capacity with the Einstein or the Debye equation, and we got before that the heat capacity is a derivative of the entropy. So theoretically, you could just integrate those equations and get the entropy. Right, so people do that. So you have the heat capacity equation integrated, you get that equation for the Einstein. So it's a discrete analytic function, and you get an integral function for the Debye. So you can calculate either one of those. Then you can play around with how does the Debye temperature change the entropy? The entropy dependence on temperature, right? So you can, that's what this is like, change the Debye temperature, and then you can calculate the entropy and how it changes with the Debye temperature. Right, so that's kind of a nuance, I guess, of this business. And then I had this thing. What is this in calorimetrically determined S high temperature? So if you determine, so you can get the Debye temperature from the entropy measurement. So if you measure the free energy and then look at the temperature dependence of the free energy, then you get the entropy. Then once you have the entropy, you can plug it into this, either this power series thing or one of those, one of these equations. And then you can back out what is the Debye temperature from it. So you can call that the entropy Debye temperature. Right. So you can get the, from a calorimetric measurement, so DSC, then you can get S. From S, you can get the Debye temperature. You can also get it from Boolean scattering, so you have some kind of spectroscopic Debye temperature. You can get it from theory, from simulations. So there's a bunch of ways to get this Debye temperature, right? It's not just one. So maybe this is a spectroscopic measured, but this is a calorimetric measured Debye temperature, and how it depends upon bond strength. So if you have more polars, fluorine, least polars, iodine, and then most polar is this is just and then this one changes the metal, I think. So it's just showing a stronger bond. The metal goes across the x-axis. So it goes like beryllium down to barium, and then it's like strongest and weakest bonds because the polarity drops as you go down like that. and then the polarity goes up. So the strongest, most polar bond has the highest Debye temperature, means it's got the highest modulus kind of thing, highest bond strength. So that coincides with that. This guy, what is this guy? Alkali metal. I don't remember. This is the same thing, I think. Just kind of the same thing. This is another, I don't remember what this is. Group contribution means you're just going to take chemical units and add them together to get something like the heat capacity. So you say, I mean, it's an organic molecule and it's got aromatic rings, it's got some kind of alkane thing. Each one has a heat capacity, you sum together the components, and each one, then you weight the component heat capacities and sum them up. So this group contribution method is throughout thermodynamics. It's kind of a cheating method to get numbers: enthalpy, entropy, heat capacity, free energy. And so the Dutch kind of invented this idea, I guess. Anyway, it's not a complicated idea. Like you have materials, especially organic materials, are made up of groups. And if you can't, some complicated molecule that you made and you want to know the heat capacity of it, you just take each of the chemical groups and then sum up the components weighted by how many there are and just get the heat capacity. And it works pretty good. I mean, it's ignoring most of the science of it, but these guys are in Germany, but the original people that did group contribution were Dutch, basically Dutch industrial people, DSM people. So then what's this stuff? I don't remember. I stuffed these into these notes. I don't remember exactly why. This one I totally don't remember. Molar volume. Somehow the Debye temperature is going with molar volume. It's in some paper, but equally skip. And then the electronic thing. So basically we had this equation in the last, I think it was the homework before the last, right? That you have this electronic heat capacity coefficient, which is in this periodic table, right? So you have the Debye temperature and then this other number, which is this gamma T. It's the gamma of the gamma T that's an electronic contribution. So any kind of vibration or motion in the material is going to absorb energy, right? So it's going to contribute to heat capacity. So it doesn't just have to be bond vibrations, right? It doesn't have to be just phonons. So it can be optical, acoustic, and it can be these like electronic transitions for like conducting materials like copper, right? And then it can also be for magnetic materials like iron. Then it's going to be, you can have magnetic contributions. The magnetic contributions are going to be weird things like this. Like you have a magnetic moment. So again, the magnetic domains are like micron size. And then you can have a spin of the magnetic moment, like a precession. And that can activate the precession of the magnetic moments next to it. So it looks a lot like a phonon, but it's a magnetic field kind of going through the system that absorbs energy. So that adds to the heat capacity. Same with electrons. So if you have conducting electrons, then you have this kind of picture of the 50%. So you have populations, density of electronic states. So the energy of the electrons versus the energy, right? And then half of the electrons, 50% population at the Fermi level. So that's like kind of taken as the highest energy of the material, more or less, right? So that's kind of a picture. This gray area is kind of the occupied electron states. And then if you go up in temperature, this thing rounds out. That's the idea. So you increase this population of things above the Fermi level, which are in the conduction band of the metal, which are going to contribute to like energy absorbing phenomena, like the electrons move when they get heated up. right? So basically that's the idea, like that this kind of change in the shape of the density of states of the electrons with temperature ends up giving you basically a linear dependence on temperature, and there's just a parameter that describes it, kind of a fudge factor, which has been modeled back with this kind of model, right? So it's something that was measured, and then just say it's linear in temperature because hand waving, like the energy distribution of electrons changes, you get more of these free electrons when you heat it up. And then because there's more free electrons, they can contribute to the heat capacity because that kind of motion of electrons absorbs energy, right? So, or stores energy. So anyway, you can say like number of electrons excited by KT, and that number is going to be related to the Fermi energy level times KT. And then let's see, if you plug this N1 back in here, you get KT squared out of this. If you take the derivative with T, you get T. So that's the T dependence, and all this Boltzmann constant squared and this distribution of the number above the Fermi level, those all get buried into this gamma number. So you could theoretically calculate the gamma number, and the linear temperature dependence follows this picture of what's going on. So for our perspective, it's just another term that adds into the heat capacity, like in that first paper of heat capacity, had that linear term in it. And it's just a number that you look up, like it's in a table. So you have the Debye, we had this equation already, the Debye cubic dependence, this is near absolute zero, and then this electronic contribution coming in. So you can see, as you get up to temperature, this thing doesn't matter anymore because the T to the 3 is much larger than T when you start cubing temperatures, right? So the T term only comes into play at the low end when you get at near absolute zero. So that thing, so the gamma, so you can measure, it's possible to measure the gamma if you have some kind of cryostat that can go to absolute zero, right? So then people do that. So then they look at, this is alloys, like substitutional alloys of palladium, ruthenium, and silver, right? And they're next to each other on the periodic table. So one has one extra electron, one has one fewer. So that means that you add an electron, somehow it gives us this shape to the thing. Actually, it doesn't make much sense, but add an electron from silver raises the Fermi level. Oh, so that, all right, so there's two things. All right, so this sounds like a little bit of a convoluted argument. But basically, they're saying that if you add an electron from the silver, the Fermi level is going to move over to the right. That means you have fewer above the Fermi level, fewer extra free electrons that are going to contribute to the heat capacity. And then they use the opposite argument. They don't say that this would move the Fermi level to the left, which would mean you'd have more. They say that because you produce a hole, then you have less electrons. So that's why it drops here. And in the middle, you have a peak. All right, you could use that same argument on that side. Anyway, you could use the same argument to argue against this thing. Either one would ruin the whole thing. So you have to kind of tie yourself in a knot to describe why this happens. But leave that at that. This is just a picture of this business of the magnetic contribution to the heat capacity. That this is the Bose-Einstein energy distribution thing, and then this is actually the Debye function, right? Yes, and then they putting in the magnetic density of states instead of the phonon density of states, and that's a picture of what happens in it. All right, so that's pretty good. So what else? So then there's a question. This is kind of going through the chapter, but basically just a little bit of a question like, why do you get a peak? So it's kind of it's like an enthalpy absorption, right? You can look at it from the angle of like so let's see. This goes back to this equation, right? So this is from Kittel, and he's describing like why you get a peak. I mean, why you get a peak is because it's an enthalpy absorption or release when you go through a transition, right? So But basically, he's trying to draw it back to this, like the Einstein equation, right? Like this guy. So he's saying there's two terms in this. The first term is temperature. So they both are going to decrease above and below the transition temperature. So one's below and one's above. That's the idea. So what does it say? First term decays as you approach the energy of the peak. And the second term increases with negative. So the second term has the opposite. So these two things compete against each other. I mean, if you have the expression for the heat capacity, so when you're doing this DSC measurement, so this is basically the heat capacity plot because you have dHdt, dQdt, and dTdt. So basically it ends up being that this is a plot of heat capacity versus temperature. So why does the heat capacity increase and decrease? That's the question. So, and the answer is that if you write the Einstein equation, the first term increases until you reach this energy. So one term increases to reach the energy and the second term decreases. So they compete against each other and you find a happy medium point when you're at the energy. So this thing is 1. And then at that point, basically you get the peak, the maximum value. So this is from Kittle's book, right? But this I think is not in the other books. So that it's also the inflection point in the free energy term, right? In the internal energy term. But it's also this peak could be described in terms of the Einstein equation having two terms, one that increases, one that decreases. When you kind of reach the peak energy, it's a maximum of that. That's kind of described in here more or less in that way. This isn't from our book. This is from that Kittle book on solid state, whatever. Thermal physics. There's two books. One's solid state material science, the other one's thermal physics. But they both say the same stuff in this context. But then there's like other weird things that happen, I guess. Like the chapter has a lot of nuanced things, right? So let's see. Metal insulator transition. This is for so iron oxide and then doping it. So well, when it's a metal, you have this electronic contribution to the heat capacity. When it's an insulator, you don't. I think that's part of the situation. So so basically there's a temperature dependence to that transition, I guess. He's talking about it in the book. So I mean, he sees a peak. So these are all things where you see a peak in the heat capacity. That's the point of this, right? So anyway, we can kind of skip that, I guess. This is this thing that's a cathode. There was one homework on this cobalt oxide, lithium cathode materials, which they go through a transition. So they're spinels. So they go through a transition of the 3+ and 2+ ionization states for the two cobalt sites on this octahedral and tetrahedral. And then basically there's a transition in that shows a peak in the heat capacity. That's in this, I mean, it's from our chapter 8. So they just show a plot of that, and it's another transition. I mean, the low temperature, this little hump here in this system is like that magnetic thing, like this spin wave thing. So when that freezes out, when you can no longer have those magnetic things, then there's a first order transition that has a peak in the heat capacity, near absolute zero. So you can't see that until you get to absolute zero, right? And then you see this big peak that's got to do with this transition going from this spinel structure to another, like I think it's some cubic structure that forms. and that's got an enthalpy associated with it. It's kind of an interesting system. It's got these peaks that you wouldn't expect to see. Notice nothing really happens to the material, it's still a crystal. So nothing happens to the material, run the DSC on it. If you can get to absolute zero, see like 2 peaks, right? So, I mean, it's interesting academically. I guess maybe it has something to do with batteries too. If you're running your battery at 1200K or at zero, absolute zero, right? Which is kind of unusual for a lithium ion. Then there's these businesses. So you can get defects in salts, right? So you can get these 2 kinds of defects, Schottky and Frenkel. So Schottky is when the two components in the salt have roughly the same size. Then you pull out a chlorine, pull out a sodium, and then you can have this Schottky defect show up. Frenkel means that you displace the metal atom. So it displaces and finds an interstitial site. So these are defects that can show up in temperature. So you heat it up, you get these defects, right? And that's going to have an enthalpy of transition too. And that's going to show a peak in the DSC curve. So it's got to do with the population, the density of states of the defect and non-defective. And then you can kind of modify the Einstein equation and just get the same kind of thing for describing those Schottky and Frenkel defect transitions. Then there's this other business. So these are kind of a little bit like research areas that people are looking at. This business has to do with something called these solid oxide fuel cells, which are, again, it's kind of a specialized area because so it's a fuel cell, but it only runs at like 1200 C, like some really high temperature. So it's of limited use. I mean, although, all right, so that said, there's thousands of people working on solid oxide fuel cells. The Department of Energy has dumped a ton of money into it. So it's not something you're going to see in your car, right? But it's something on a fixed. So they have high efficiency, and they don't have a liquid electrolyte. So they're using a solid electrolyte, and when you heat up these salts to that kind of temperature, the metal becomes like a liquid. Basically, the metal ions can flow like a liquid. Then you can have a fuel cell or a battery that uses that. Like it could be a lithium ion or silver. So anyway, so the transition from fast ion conductor to non-fast ion conductor is also leads to a peak in the heat capacity. And that because people are making these fuel cells with it, then they want to know about that too. So that's in the chapter. So it depends like what we had the guy Raj Singh, right, that gave the talk like a couple of weeks ago. So this is stuff he did. He did this fast ion conductors for high temperature fuel cells. He talked about diamonds or something, but basically for a while, this was the only thing he was doing because the Department of Energy was just giving out $100,000 checks for it, like without any problem. I think they still are, but basically you need a kind of a high temperature oven and a couple other things to do it. Anyway, so then this stuff in this chapter about there's only 2 other things. It's 5 minutes, but tempting to just anyway. So anyway, the glass transition is another thing, right? So in the DSC, so we saw like glass transition is going to be this kind of knee thing, and you can get an overshoot on it. So you can, if you heat fast, so you're going from a glass to liquid. If you zip through it, you'll get a spike here that looks a lot like an enthalpic transition. So it's kind of like the material gets stuck and then it releases, and that release, it can lead to something that looks like an enthalpy. And you can get kind of the same thing on cooling, right? So people have spent a lot of time, because it's an esoteric subject and no one knows the answer. It's basically glass transition. You could spend a lot of time doing it. People have spent a huge amount of time, the French especially. So the French invented this fragility idea about glass transition. And then some Americans picked up on it. Naval Research Lab they've been studying fragility and glass transition since the 1950s or something, right? So they're still going strong at it. So I'm not sure what the answer is to it, but basically, we talked about Kautzman paradox. Like if you plot the entropy of the liquid, and then you can supercool it, right? And then it could actually cross over where you'd have like the solid phase, and that crossover point would be like the Kautzman temperature, TK, where it's a paradox because you couldn't have a liquid with a lower entropy, like less order than a solid. So it can't possibly happen. And then, so this is kind of a plot of like what the absolute glass transition, if you could cool it the slowest you could cool it, that would be the temperature where it would have to form the glass because it's thermodynamically not possible. And we looked before, like you can calculate the moduli and things, figure out that can't be possible due to you'd get a negative modulus if you did that, things like that. But so anyway, so let's see. So it's just some discussion about, because heat capacity is dsdt, you can talk about the entropy, how this has to do with vibrational degrees of freedom and things. Maybe I'll go through this a little bit more better like later on, but basically you're going to end up with this kind of fragility idea. So it's fragility, we got a minute. So fragility has to do with dynamics, right? So you can say like at the glass transition, the viscosity goes to infinity. So it doesn't flow anymore. And it's a liquid. Above that, it has a viscosity. Viscosity follows an Arrhenius function. It's like the classic thing, it follows Arrhenius. So there's an activation energy for the atoms to move. As the temperature goes up, they move easier. So it's exponential, like a Boltzmann factor, and you get the viscosity. Then you have some zero temperature, which would be like where this stops moving, like the viscosity at some fixed temperature. So in that case, you'd say like T minus T Vogel temperature, and this would be the viscosity at the Vogel temperature. So T goes relative to some 0 point where the viscosity goes to infinity. Anyway, so if you're away from the glass transition, then you can plot this kind of log of viscosity versus the 1 over the temperature, because you have 1 over T here, and then you can get the slope of that, right? So it should be linear, right? This would be a linear equation. Log of viscosity would be 1 over T, straight line. So it's called a strong glass. And then you can have what's called a scaled exponential. So a lot of things don't follow that. So you put in a fudge factor, you raise this temperature to a power m, and m is called the fragility, like m's log of the viscosity or whatever dynamic thing you're talking about to measure the glass transition, and then over change in 1 over T gives you this m number. So this would be, m would be like 1. So m would be 1 if it's a strong normal glass following the Arrhenius function. And then m will be something less than 1 if it's a fragile glass. Right? So this is a French idea of things here. Anyway, so this is like a Nature paper, 1999, I guess. I forget where these people are, but basically looking at, for a variety of glasses, talking about the fragility of these things, like how you get this fragility number. So it has to do with heat capacity, because it has to do with entropy, because it has to do with some kind of discussion about the ordering that happens when you get through the glass transition. So I'll probably like go through this next time. I'll go through that, and I'll go through something about the glass transition, and then about the heat capacity of polymers. That's like 2 slides. So we should be able to do that pretty fast. And then I'll go through that homework in a little bit of detail, like whatever the questions are, that paper. So that should take the whole class next time. Then we're done with heat capacity. Just bury it. Never think about it again. Until one day. Someone comes knocking at your door.
I think Karen and I have it covered between us, but we just need to look back over AMT.